Okay. Are you all right now?
Yes, sir.
You are late for another minute or two. I will phone your mother already.
Oh, and the toilet, sir. Sorry.
You're supposed to do all your business before you come for tuition, not using the tuition time
Yeah,
for toilet.
yes, a bit late. Yeah, teacher can.
Okay, let's carry on. As I say, it's better for you to review through what I teach you. Then you can participate in class. That is more efficient way. Rather than forget everything and then review again. Right? You need to help yourself, reinforce. I teach you, do the homework, force it in faster. Rather than forget and then start to learn again, take long time. Okay, our next topic is wave particle duality. Okay, wave particle duality. Okay, this is just a cartoon. Right? They blaming each other. And Schrodinger come up with a solution. Right? Page 224. We want to state the Brody's hypothesis. Use the relation lambda is hp, calculate the Brody wavelength, interpret the electron diffraction pattern as an evidence for wave nature of electron, explain the advantage of an electron microscope as compared to optical microscope. What does it mean by new nature of light? Idea of light being wave motion and idea of light being particle motion are merely two different models which help us to explain the behavior of light. Neither is necessarily a literal description of what light is. Right? We need both of them to help us understand the nature of light. Wave particle duality. Duality means having two different nature. Properties of particle are the mass, right? The size, that means the volume or the volume, then kinetic energy and momentum. And then we have studied photoelectric effect, our first subtopic, appearance of line spectrum, and production of X-ray, which is our next few topics after this, shows the particle nature of electromagnetic radiation. That means we think of electromagnetic radiation as normal waves, but as particle, photon. Properties of wave are frequency or wavelength and amplitude, right? Interference, diffraction, and formation of standing waves show the wave nature of electromagnetic radiation. Okay, so this one summarizes for you, particle or wave. Physicists have come to terms with the dual nature of light. This duality is referred to as wave-particle duality of light. Right? Have two different nature. Light interacts with matter as particle. The photon. Light travel through space as wave. Question, of course, the next question is, if that is true, then electron is a particle. Can it behave as wave? Right? De Broglie come out with a solution for the De Broglie equation. Right? De Broglie imagined the electron can travel through space as wave, but interact with matter as particle. De Broglie's relation gives the relationship between wavelength and momentum of the particle. Right? So if electron is a particle and it travels through space as wavelength, as waves, then we should be able to measure the wavelength. Right? That is de Broglie's equation. Wavelength equals to Planck's constant divided by momentum. So the equation gives the wavelength. of the particle when the momentum is known. The wave associated with the electron are referred to as matter waves. Right? H is your Planck's constant. E is your momentum. History. The Brody hypothesis formulated in 1926 predict that particles should also behave as waves. The Brody's formula was confirmed 3 years later. Right? Come up with his theory. Then you must have experiment to confirm it. Then you know that your theory is correct. 3 years later, for electron, which have a rest mass, right? Electron we think of as particle before that time. So it has a rest mass. With observation of electron diffraction in 2 independent experiments at the University of Aberdeen, George Paget Thomson passed a beam of electron through a thin metal film and observed the predicted interference pattern at Bell Lab, Clinton Joseph Davison, and Lester Howard Turner. So this is the main person. This is probably the guide. Right? He's the main person to do the experiment. Guide a beam through a crystalline grid. So can either pass it through thin metal film or crystal grid. Crystal basically, thin film is much thinner than the crystal. So they were both of them, Thomson and Davison, shared the Nobel Prize for Physics in 1937 for their work. This is just extra information for you. Okay, diffraction of light through a circular aperture. This is just formula to remember that. That's your theta. Our theta is this one. That's why it's 2.44, double that, right? Rather by 1.22. For diffraction to occur, diameter of aperture must be about the size of the wavelength. Right? That size there, aperture, must be roughly equal to wavelength. Then you can see diffraction. Greater the wavelength, greater the deflection. When we say deflection, in this case, we are saying that this angle, or that diameter. If you imagine that is your center, that's your radius. That's your radius. So that S becomes your arc length. So arc length equals to R times theta. R is this radius, theta is this theta. Okay, so greater the wavelength, greater the deflection, greater this angle, or greater the diameter of the bright spot. Okay, electron diffraction. When X-ray, this is X-ray from the X-ray tube. You want to reduce the wavelength. Okay, certain wavelength you want it to pass through. You want all the different wavelengths to pass through. When X-ray are directed onto a thin metal foil, we see diffraction pattern. Right? In this case, you can use crystalline solid DNA. Electron can be shown to behave as wave. Right? That's our own experiment we can do in laboratory. Let's go. There's your cathode. Right? Heated by a low power source, so the electron is emitted. The cathode is charged negative. The anode is charged positive. Right? By this accelerating voltage. And that tube is called the electron diffraction tube. Right? Basically, inside there is a vacuum. Right? So the electron beam is emitted in vacuum. There's your carbon film. There's your anode. Right? It's charged positive. There's your fluorescent screen. So where the electron hit the screen, you will see a bright light there, a bright spot there. Right? Electron gun, that's your electron gun. Produce a beam of electron, that's a beam of electron. They are accelerated by the anode. So after acceleration, this is constant velocity coming out. right? This high potential. Changing the voltage V, that voltage, that one. The energy and thus the speed of the electron can be changed, right? We increase V, increase the setting voltage, so increase the energy or velocity of the electron passing through. What do we observe? There's a pattern that we observe. Beam strike the carbon target. Right? There's your carbon film or carbon target. And diffraction pattern appear on the screen. That is your screen. Right? Like your CRO. So that is your pattern that you see, concentric circle. Pattern of concentric ring observed on the screen. If the electron is emitted from the cathode with zero velocity, usually we assume that it has emitted from cathode with zero velocity, then we can do some calculation. Passing through the anode with a potential difference of V, there's a potential of the anode. Then we are just using this is our work done, right? Electron charge accelerated by a potential V, and that energy becomes the gain in kinetic energy, half mv squared. M is the mass of electron, E is the charge of electron, right? Higher V, accelerating potential, higher speed, or greater momentum, right? Greater momentum. So you have shorter wavelength, right? From de Broglie's equation, greater momentum, smaller wavelength. So smaller the diameter that you see on the screen. No? Okay, just refer to the note that I just given you. Right? Shorter wavelength. This one is smaller. So diameter becomes smaller also. Okay, so that is the pattern that we see. Electrons are diffracted by the carbon atoms and the spacing between the. So this one is trying to explain to you why. Because right, instead of aperture, now the aperture is a spacing between the atoms. Right, which is roughly the atomic layers of carbon behave like diffraction grating with many slits. Electrons show diffraction effect because their wavelength, their de Broglie wavelength lambda is similar to the spacing in atomic layer. Okay, that's how we get our diffraction pattern. So we will study this later on. Right? For this case, under Bragg's equation. Okay, now we are just studying that. Right? Where the spacing that's your spacing, right? Between the atoms. Increasing the voltage, as we have gone over that, just to go with you on the mathematical side. That's the equation. There's the voltage there. So increasing the anode voltage makes the pattern shrink. Right? You can observe it. The diameter becomes smaller. Electrons have greater kinetic energy. Yeah. Greater voltage, greater accelerating voltage, greater kinetic energy. Right? So greater momentum. Right? Greater momentum. So smaller wavelength. Shrinking pattern shows that their wavelength has decreased. Right? P of electron, work done equals the gain in kinetic energy. Yeah, that's what we derived just now. So for circular aperture, we use 1.22 lambda over A. Okay, remember that is your theta. The theta here is different. No? Don't get confused. Right? The theta here is two times the previous theta. Right? That's why you times 2.44 lambda. Okay, so it can be a bit confusing, but don't get confused with the two. Okay, so that theta is this one. The previous theta is this angle, is 2 theta. That's why it times 2 here. And remember that equation there, S equals to R times 2 theta. If you use that theta as Theta. Okay, let's do some calculation. I hope you'll do some calculate. You'll study tonight and do some calculation. If not, you'll see stars tomorrow. Okay, calculate this one using the equation. An electron is accelerated to a potential of 5 kilovolt. Calculate the de Broglie wavelength of the electron. Okay, calculate. Basically, we are just using this equation and that equation. Go and calculate for me. It's in your worksheet number 4.
Okay.
Right. Calculate your speed first. Okay, got the answer? Find the speed first. Then after that, use the de Broglie equation to find your wavelength. Yeah, put in your value. Make sure you bring your constant value or constant review every time you come for tuition. Then can refer and do your homework. I can't learn for you. You have to learn yourself. That's your charge on electron. That's your potential difference. One, change to SI unit. That's the mass of electron. Okay, should be able to get the speed as 4.19 × 10 to the power centimeter per second. Okay, what is the wavelength? Can you get the answer? You should get 1.74 × 10 to the power minus 11 meter.
Yeah, I got that answer, sir.
Okay, good. Right, to compare to wavelength of light, right, about 6 × 10 to the power minus 7, you can see that this one is much smaller. 3.4 × 10 to the power 4 times larger. Right, this one. That means this one is smaller lah. Right, because this is mainly X-ray. Right, probing matter. High-speed electron, this uses up. Right? High-speed electron from particle accelerator have been used to determine the diameter of atomic nuclei. Right? Why from particle accelerator? Because the speed is high. Speed of electron is high. This is possible because the high-speed electron have wavelength of the order of minus 10 to the power minus 15 meter. Wavelength is similar to the atomic nuclei. Ordinary bodies have very short wavelength. Thus, the wave nature are not shown by them. Right? Let's try to calculate out using the formula. Calculate out for me. What is the wavelength? What is the de Broglie wavelength for a bullet of mass 30 grams? moving the speed of 320. Remember to change your gram to kilogram. Calculate your wavelength. I've given you the Brody formula. Right. First, find your momentum. Then calculate use your de Broglie equation. Calculate your wavelength. Can get the answer?
Can, sir.
Any comment?
No, sir.
The comment is very simple. The wavelength, right? Wavelength is very, very small. You can't get this small size. So for a bullet moving, you cannot show its wave nature. There's no way you're going to show the diffraction because you have to have a hole that small. And for a hole that small, the bullet cannot go through. Right? Bullet is too big. Wavelength of bullet is very small. It's not possible to make a slit so small. Besides, the bullet is unlikely to be able to pass through. Of course, if you pass through, it will damage the slit. But what we are saying is the bullet size is too big compared with the slit that is supposed to pass through. So there's no way you can show the wave nature of the bullet. Okay, try this one. This is your first term work. Show the particle of mass m and momentum p has a kinetic energy of k equals to p squared over 2m. Okay, can start with your kinetic energy first. And momentum is nv, p equals mv. Yeah. Number 6 in your worksheet. Can or not? Yeah, start with kinetic energy formula. Right? Multiply by m, multiply by m, divide by m. Can get? Can or not? Can or not? Can or not? This one you must know. This is your first semester work, first term work. Anything not clear? Which part is not clear? Yep. Which part you don't understand?
Understand, teacher. Understand.
Let's do the next one. Number 7. Derive the formula. Particle of mass m and charge E is accelerated through a potential difference of V. Show that the wavelength of the particle is. Right? Use the de Broglie equation. We are just going through this part, that's all. The equation. That's all. And that equation, these two equations, that's all. We are just using these two equations. I'm hoping tonight you do put an effort to learn. If not, I can't help you with it. Review through tonight what I teach you, so that tomorrow you can solve problem for me.
Okay, sir.
Checkpoint 24.3, 24.2, you still got 2 questions to do. Right. Start with kinetic energy formula. Right? Convert to momentum. Can or not? Why take so long one? Then replace your momentum with the de Broglie equation for wavelength. That's all. Right? You square P square H square lambda square, and then there's your 2m. Right? And use that equation. Work done equals to maximum kinetic energy. Okay, remember that kinetic energy. There's your kinetic energy. Put that one there. Okay, that's what we are doing. Right? The equation there, kinetic energy is this one. Maximum kinetic energy is this one. Put there. Then take your lambda across. Take your EV down. And square root it. That's why we get the answer. Anything not clear? Well, do your equation, do your calculation, and then compare with my answer. We're not going to go any further. Let you digest and do your homework tonight. Tomorrow you tidy out all the homework. Can any part not clear? Yep.
Clear, sir.
Anything else you want to ask? If not, we'll stop for today.
Stop for today.
Anything else you want to talk or ask?
No, sir.
No, then I will stop here or end here now.
Okay.
Okay, see you tomorrow, 9 o'clock.